Hi, and welcome to 8.1b Work 2. So in this one, we talk about work some more, and we derived a new formula for work in class, which I'll do for number 1. It says a student applies a 20 Newton force to move a crate at a constant speed of 4 meters per second across a rough floor. How much work is done by the student on the crate in 6 seconds? So you might start by doing your guess method here. So it's 20 newtons of force. Now the speed or the velocity is 4 meters per second, and it's a rough floor. It doesn't say anything about friction, so we just know that the force that they're exerting is 20 newtons. And it wants to know how much work is done by the student on the crate in 6 seconds. How much work is being done? Well, we might want to do W is equal to F times D, but they don't tell us a distance. They just tell us a velocity and a time. Well, we could figure out what the distance is. We could do V is equal to D over T, and then we cross multiply and you get D is equal to V times T. And now at this point, we could plug in the velocity and over here and the time over there, and the distance would actually be 24 meters. But the cool thing is we derived a formula for this. So now that we know instead of distance, we know we could do the velocity times the time. What you do is you take this quantity and plug it in over here every time you see a distance. So let's do that. It says work is equal to the force times velocity times time. This is a useful formula that we'll use for a few questions in this homework assignment. So work is equal to 20 times 4 times 6. So the work done is equal to 480 joules. Again, you could have solved for the distance first and plugged it to our good old formula W equals FD, but it's good to derive equations every once in a while. It makes your life a little bit easier. So we could use that now. That's in the toolbox. Number 2, Zip the monkey pushes his crate of bananas with a force of 15 newtons. How far has the crate gone? So they're looking for the distance. If Zip exerts 300 joules of work on the crate. Okay, good. So this is just a straight up W is equal to FD problem. So 300 is equal to 15 times D. D is equal to 20 meters. Pretty straightforward. Number 3, a student exerts 750 joules of work when pushing a crate across a horizontal floor. If the student pushes the crate with a constant velocity of 10 meters per second, for 20 seconds, it should say, instead of. So the time is 20 seconds. There's a typo there. How much force are they exerting on the crate? Okay, so now this is another one. They give you the work, but they don't give you the distance. They just give you velocity and time. So we should use this other formula that we derived. FVT is equal to the work. So 750 joules is equal to the force times how fast you're going times the amount of time you're exerting this force. So so we could solve it out from here. 750 is equal to 200 F is equal to 3.75 newtons. Alrighty. Number 4, how much work is done on a 30 kilogram block when pushing it with a force of 60 newtons over a distance of 20 meters? So you're pushing a block, the mass of the block is 30 kilograms, but you're not trying to overcome gravity here. You're just pushing it across a level floor. So you want the force is 60 newtons. So this is just excess information right now. And the distance is 20 meters. They want to know how much work is being done. If it said you lifted up the block, then you might have to find the weight of the block. But they don't tell you that. So it's just W is equal to F times D. So W is equal to 60 times 20. So W is equal to 1,200 joules. That's the amount of energy you're expending in pushing this 30 kilogram block over that distance. Number 5, how long does it take to do 500 joules of work on a block when pushing it at a constant speed of 7 meters per second with a force of 25 newtons? How long does it take? All right, so you're doing some work. The amount of work you're doing is increasing with time. How long until you reach 500 joules of energy that you did? 500 joules of work. So W is equal to F T. 500 is equal to 25 times 7 times T. So 500 is equal to 175 T, and then T is equal to 500 divided by 175. So it's like 2.8, we could call it 2.9 seconds when you round it. So it takes 2.9, if you're pushing with this much force and you're moving it this fast, if you're pushing with this much force and you're moving it this fast, you need to do work for 2.9 seconds before you get to 500 joules. Okay, number 6. As shown in the diagram below, a 20 Newton force is pulling an object up a hill at a constant rate of 2 meters per second. What is the work done by the force in pulling the object from A to B? All right, now with these work problems, you always want to check, is the force parallel to the displacement? In this case, they're telling you the force here. The displacement from A to B is in this direction. So this line is parallel to this line. So it makes our lives a lot easier. We don't have to do trig. We don't have to worry about it being on an inclined plane. We could just do pretty much business as usual, because yes, the force and the distance, they're parallel to each other. I should say displacement. Okay, so the force being exerted is 20 newtons, and the displacement is 30 meters. Again, they're in the same direction. They're parallel to each other. And they want to know the work done. So all you have to do is W is equal to FD. 20 times 30. W is equal to 600 joules. That's the amount of work you're doing. Number 7. A worker pushes a 75 Newton copper block with a horizontal force of 40 newtons, a distance of 20 meters across a horizontal steel floor. What is the frictional force acting on the block? All right, so we could draw ourselves a free body diagram here. Here's our copper block, and they're pushing it with a force FA is 40 newtons. If the applied force in this direction is in that direction, the frictional force must be acting against it. And there's a weight, and it's on a surface, so there's a normal force. And those two forces, the weight and the normal force, are going to be equal to each other. They're asking for the frictional force. Well, the frictional force is equal to mu Fn. Now, is this static or kinetic friction? Well, it's sliding across the floor, so it's a kinetic friction. Let's see, what else do we know? The weight of the block is 75 newtons. It says it's a 75 Newton copper block. That means the normal force is also 75 newtons. And the coefficient of friction for copper on steel is, let's see, copper on steel, kinetic, 0.36. So we're looking for 0.36 over here. That's the coefficient of friction. So the frictional force is equal to 0.36 times the normal force, which is equal to the weight of the copper block, 75 newtons, and the frictional force is 27 newtons. So that's the frictional force. Okay. It says, what is the net force acting on the block? Well, in the y direction, these two forces are balancing each other out. So the net force in the y direction is 0 newtons. But in the x direction, you have this frictional force and this applied force. And as you can see, the applied force is greater than the frictional force. So they don't balance each other out. They don't cancel each other out. They're unbalanced. There is a net force acting on the block. The net force, by definition, is the sum of the forces. And right now, we're just looking in the x direction. So don't be afraid of this like sigma thing. It's the side, this weird e, this weird 3. It's just the sigma is a Greek letter for, they use it in math to represent the sum. So when I write that, it shouldn't be like daunting. It shouldn't be confusing. Hopefully it's a reminder that it's the sum of all the forces, because the sigma means sum, right? So we're just adding the forces together. This is a review of what we did in the past. So the way we drew our diagram here, the 40 newtons is pointing to the right, so I'm going to keep that positive. And the frictional force is acting against it. It's pointing to the left. So I'm going to make that negative. And the net force is equal to 40 minus 27, 40 plus negative 27, which is 13 newtons. So when you add all the forces together, you get a net force of 13 newtons pushing it to the right. So now it says, what is the net work acting on the block? Well, we could redraw our diagram if we wanted to. Now that we know what the net force is, it's almost like we could think of it like there's only one force acting on our block. And it's going a distance of 20 meters. So here, this is 20 meters. So what is the net work being done on the block? Well, we could just do work is equal to F times D at this point, because we know the net force. So net work is going to be equal to 13 newtons, the net force, times 20 meters. So the net work is 260 joules. So that's one way to do it, and that's my preferred way because it's only one equation. However, if you wanted to go back to the situation where we're looking at all the forces like that instead, again, the weight and the normal force are canceling each other out. So we don't have to, we could do that, but they cancel each other out. So for simplicity's sake, let's just look at the frictional force and the applied force. We could figure out what the work done by the applied force is and the work done by the frictional force. And what happens is you get W equals FD, and there's this thing, cosine theta. Why is it cosine theta? That's basically making sure that the force is acting parallel to the displacement, and it also tells you if the force is positive or negative. So here the displacement is going in this direction, to the right. This applied force is acting exactly in the same direction as your displacement, but the frictional force is acting against you. It's a force pushing against you. It's actually doing negative work. All right. So we do that by saying that it's a 180-degree angle, and cosine of 180 gives you a -1. So it looks like this. The net work is equal to the work done by the applied force plus the work done by the frictional force. And when you plug in our formula, FD cosine theta, FD cosine theta, but this is for the applied force, this is for the frictional force, the net work is equal to 40 times, you're still going 20 meters in both cases, In this case, it's cosine of 0 degrees for the applied force because you're moving along with the distance. Cosine of 0 is 1, plus the frictional force times 20 times cosine 180 degrees, which will give you a -1, meaning you're doing negative work because you're working against your movement, really. You're pushing a force against the direction that you're going. So the net work is equal to 40 times 20 times cosine 0, which is 800 joules, plus 27 times 20 times cosine 180 gives you -540 joules. Again, your force is totally opposing your displacement. You're doing negative work. So the net work you're doing is equal to 800 plus -540. And you get the same answer, just 260 joules. All right, same answer as before. So you could think of it either way. You could either just look at the net force and figure out, okay, I went 20 meters with my net force of 13 newtons. Or you could think of it, instead of looking at the net force first, you could kind of look at the net force and the net work all in the same equation here. Instead of doing the net force up here, you're doing it all in the same equation with the work formula. But now instead of just adding two quantities together, we're also calculating what each quantity is with our formulas like that. So, either way you look at it, it's good physics. All right, have a good day.